Morning, everyone. Just out of interest, how many people have heard of quantum computing before? Okay, a lot of you have heard of it. It's been in the news a lot over the past, particularly 6 months, 6 to 12 months or so. So for those of you who haven't heard of it, and even for those of you who have, so quantum computing is a completely different approach to computing than our regular classical computers that are built on Boolean logic. Quantum computers derive their power from the strange logic that exists at the microscopic level, the behavior of things like atoms, electrons, photons, and so on. So just to contrast the behavior of an electron, let's say, with the behavior of everyday objects that you're familiar with, let's just contrast the journey you had here this morning with the journey that an electron would take. So this is a map of the local area, and you'll see my high-tech demo here. So we've got you arriving down in your bus. There's a junction on the right. It's a one-way street, so you can't go up it. So I hope you all went straight on up Queen's Road to the junction and turned left around to the car park. Maybe some of you didn't come that way. Maybe you came a different way. But the point is that all of you followed a particular path here. Your route can be described as going along one road, then going along another road, and so on. What about an electron or some other, atomic particle? How would an electron get here? So let's position the electron back at the first junction there, where there's a road on the right. First of all, we'll say that electrons don't really obey the rules of the road. They don't know the highway code, so it might turn right here up that one-way street the wrong way. They also travel pretty fast. They break the speed limit. So we're going to set up a couple of speed cameras along each road to keep an eye on them. And that'll tell us which road the electron went up. So what would we observe? Well, we'd observe either the electron went up Queen's Road, that we all traveled up. The speed camera there would flash, detect the electron traveling on that road. Or the other camera would flash and detect that it's traveled up the other road. And if we had a series of electrons traveling up the road, either one camera would flash or the other camera would flash. We would never get a situation where no camera flashes. It has to travel up one of the roads. And we'd never get a situation where both cameras flash at the same time. So probably not really surprising yet. However, suppose the cameras were out of action, or we cover them up, we're not using them. The point is that we're not observing the electron anymore. How would the electron travel from the junction it's at up to the next junction? So this is where things get a bit strange. The electron actually behaves in such a way that it appears as if it's traveling up both paths simultaneously. It takes both roads in a sense. And we can perform experiments in the lab that confirm this type of behavior. It's sort of like a wave-like behavior, and we can infer this wave-like behavior by the fact that there's interference. So if you've studied waves in your physics classes, you might have come across this term interference. So that's quite strange. The electron behaves differently if we're watching it than if we're not watching it. So who's this chap I've put up on the screen? So this is John Bell. He's a quantum physicist. Born in Belfast, he did some extremely groundbreaking work on quantum mechanics in the 60s and 70s. And this road on the right here, I haven't mentioned its name yet, but it's called Bell's Theorem Crescent. So that road is obviously named after John Bell. Actually, it's named after his theorem, Bell's theorem, which has been described as the most profound theorem in all of science. It actually disproved one of Einstein's hunches about how the universe actually works. So to honor John Bell on I think it was on the 50th anniversary of his paper, Belfast City Council, I think they missed a trick. I think they should have just put another L in Belfast to honor him, but instead they named this road Bell's Theorem Crescent instead. So that goes round, that's very appropriate, that road, because it goes round Belfast Met, and John Bell actually went to Belfast Technical High School, which I think was the forerunner of Belfast Met. The quote here that John Bell's given us, so this isn't what John Bell is famous for. I've made this quote up to match the slide. But John is telling us that in quantum mechanics, if a particle wants to go from A to B, and there's different routes, it will actually, if we don't observe the particle, it'll go by all possible paths. So that's quite strange. When a particle is in that sort of state, we describe it as a superposition, a quantum superposition. Now this year, 2025, is actually the UN International Year of Quantum Science and Technology. Why this year? Well, it's considered to be the 100th anniversary of the birth of quantum mechanics. So in 1925, this guy, Werner Heisenberg, who you might have heard of, wrote a paper that was deemed to be the birth of modern quantum mechanics. It had been around for about 20 years before, but the whole thing was reset by Heisenberg's work and others. This quote by Heisenberg actually sums up some of the very important things about quantum mechanics that are relevant to quantum computing, which I promise I'll get onto in the next slide. So this quantum superposition, sort of, what is it? You know, it seems very strange. Does half an electron go up one road and half the other? No. What does happen up these two roads? And what do we even mean by the word happen? So this is where it starts getting a little bit philosophical, and we can only talk about what happens. Obviously, if we watch something, if we observe something happening, we can say something's happened. But between our observations, we can't say with any certainty what's happened. And so it's only really possibilities of things that could happen. And really, we talk about the probability of the particle going up one road or up another road. And what happens doesn't actually happen until we observe it. So how does this relate then to quantum computing? So these quantum superpositions are very strange, and when we harness their power through qubits, that's what gives us quantum computers and allows us to do things that are otherwise impossible. So in classical computers, obviously, they're built on Boolean logic, which operate with classical bits. Classical bits can only take two values, 0 or 1. So a bit like can only go up Queen's Road or Bell's Theorem Crescent, one road or the other. The qubit, also, if we measure it, can only take two values, 0 or 1. It's a bit like the electron. If we measure a qubit, it's a 0 or a 1. It goes up one road or the other road. When we don't observe the electron, or we don't observe the qubit, it can exist in a superposition, so some sort of weird mixture of 0 and 1. That superposition actually is a vector that can point in sort of multiple different directions, and the exact direction gives the probability that we're going to observe a 0 or a 1 when we come to make a measurement. Now, we can't do much with one single bit, and we can't do much really with one qubit. But we can start doing interesting things with multiple bits or multiple qubits. And even if we have 2 bits, well, if you've learned sort of binary numbers, you know that with using 2 bits, we can represent 4 numbers, 0, 0, 0, 1, 1, 0, 1, 1. And those could represent, say, 4 solutions to a particular problem that we're trying to solve. Classical computers, each 2-bit system, each collection of 2 bits, encodes just one possible solution. So 0, 1, for example, encodes the second solution there. However, with a pair of qubits, we don't have to force it into one of those 4 states, 0, 0, 0, 1, 1, 0, 1, 1. It can exist in a superposition of all 4 states. So it's one pair of qubits can encode all possible solutions simultaneously in a superposition. However, whenever we come to measure the 2 qubits, we're going to get one of these 4 results, one of the 4 potential solutions. For example, 0, 1, you might get. Each solution occurs with a certain probability that's determined by the direction of the vector that represents the superposition. So how do algorithms work? Well, classical algorithms work by just trying out different 2-bit solutions until we find the solution that we're after, the one that solves the problem. Quantum algorithms, however, they work by manipulating these quantum superpositions. So we can do things, just like we can manipulate bits using ands and ors and things like that, we can manipulate superpositions, we can rotate them and reflect them and do clever things like that there in a way that maximizes the probability that when we come to measure the qubit, we get the solution that we're after. And going back to the previous slide, Heisenberg's quote, although in that superposition we're looking at all different possible solutions, we're not actually, those solutions don't happen until they're not evaluated until we make the measurement. So we can do things using solutions before they've actually really happened. Let's look at a couple of examples of problems that you can solve with quantum computers. So I'm just going to look at the 2 most famous problems. So one is factorizing large numbers. So do you all know what factorizing is? Factorizing numbers? Yeah, do you know what prime numbers are? Yeah? Okay, let's start off with an easy one then. So let's factorize the number 15. Let's just check your knowledge. So what's the prime factors of 15? Anyone? 3 and 5, yeah. 3 times 5. Don't know why it's called like that, but 3 times 5. What about 91? Slightly more difficult one. Anyone? It's a little bit trickier. 7 times 13, okay? You see it gets a bit more tricky as the numbers get larger. So what about this number here? I'm sorry, these seats probably block out some of the numbers at the bottom, so you won't be able to actually do this one, but any ideas? Obviously it's, oh, you can see it up there, yeah. You can do it after all. No, it's going to be too difficult. How long do you think it would take the world's most powerful supercomputer to factorize that number? Who thinks it would take, say, something less than a year? What about 10 years? We got the world's fastest supercomputer and give it 10 years to solve that. Would it solve it? A million years? Would it do it in a million years? Best estimates are that it would take the best supercomputer 300 billion years to factorize that number. So that number is the product of two prime numbers. So, the age of the universe is estimated to be about 14 billion years, so we're well above that, about 20 times that. Quantum computer, how long do you think it would take a quantum computer to factorize that number? Exactly, about 10 seconds or so. So you can see the difference in power that quantum superpositions and qubits give us. Why is this? Well, we're changing the complexity class of the problem. Classical computers, we can measure how long an algorithm is going to take as a function of the input to the algorithm. And the best algorithms for factorizing large numbers or exponential. So it's an exponentially difficult problem for classical computers. So it's 2 to the power of n, which gets large extremely quickly. On a quantum computer, however, the execution time scales by n squared, which is much, much less. And if we go to extremely large n, these graphs are just going to be nowhere near each other. So this is, you've probably seen headlines like this, regarding quantum computers in the popular news. So back in December, for example, Google unveiled its Willow chip. And, the headline there was that it completed a task that would take a classical computer 10 septillion years, I think that's 1 and 25 zeros after it, to solve a problem. Well, it solved it in about 5 minutes. And, as if that's not impressive enough, if we've got any science fiction fans here, Google claimed that this leads credence to the notion that quantum computation occurs in parallel universes, in line with the idea that we live in a multiverse. So, like I said, quantum mechanics is a bit strange. There's different interpretations of it, and that's just one interpretation of it. Just look at another problem then that is impossible to do efficiently on a classical computer. Imagine we've got a filing cabinet that's got 1 million drawers in it. One drawer contains a bar of gold. All the other drawers are empty. So roughly, how many drawers are you going to have to open to find the gold bar? If there's 1 million drawers, roughly how many do you think you would have to open up? On average, it's going to be about half of them, so about 500,000 drawers. Quantum computer, only about 1,000 drawers. So much, much, much more efficient. If there are 4 drawers, actually, a quantum computer can do it in even just 1 iteration, which is absolutely amazing. Okay, so the exciting thing about quantum computing is that we're really just at the start of it, and applications are beginning to appear, and commercial applications. So there's lots of existing jobs in quantum computing, but by the time you enter the jobs market, some of you enter the jobs market, there'll be new jobs that just don't exist at the minute. So there's jobs with the physical aspect, with building quantum computers, writing code, optimization, financial side of things, drug design, and then there's the overlap with AI. So if you are interested in quantum computing, just thought I'd end with a little bit of advice. My advice would be read up on it, find out a wee bit more about it. Popular science books are a great way to do that. And there's lots of popular science books on quantum computing and quantum mechanics generally. Consider maths, physics, and obviously computer science as options as you go through your education. Quantum computing is at the overlap of all 3 of those subjects. Try out some code. You can actually run some code yourself, write code and run it yourself on quantum computers now. So IBM have a quantum toolkit called Qiskit, and there's 6 quantum computers that they own, and you can run your code on that. I wasn't brave enough to do a demo this morning. But most importantly, follow your curiosity. There's lots of different directions within quantum computing, and behave like an electron and take every path until you need to settle on one. Okay, so I'll leave it there. Thanks very much, everyone.